Hi everyone, in this video I want to introduce you to a new type of problem that would require you to utilize a skill you learned from the last chapter, which is stoichiometry, and combine that with the ideal gas law that was covered in the last video. So let's just go straight into an example problem. So here I have an example problem, and as always I want to identify what variable I have and what variable am I missing. So recall the four different variables that involves in all gas laws, and those are pressure, volume, mole, and temperature. So I am going to start just reading the problem and then identify if I have any of those four. So the question is asking me to calculate the volume of oxygen gas. So here's volume, I'm going to write that's V, of oxygen gas produced at 1 atm, so that's P, and 25 degrees Celsius, so that's T, by the complete decomposition of 10.5 gram of potassium chlorate. I'm going to change color now to identify the 10.5 gram of potassium chlorate because this piece of information is the only one that belongs to a different chemical. So temperature, volume, right here, temperature, volume, and pressure, all the one that's in blue, all the variable that's in blue belongs to oxygen gas. So they belongs to oxygen gas. But the information of 10.5 gram is the only one that belongs to potassium chlorate, which is not oxygen gas. So here's potassium chlorate, and I have in blue is oxygen gas. All right, now this is how you know you need to do stoichiometry, is that you have some variables belonging to one chemical, and you have some, or in this case it's one variable that belongs to a different chemical. So if you want to use the equation of PV equals to nRT, you have here pressure, so that's pressure, and they're asking for volume, so that's what should be my missing variable. Then look for N. You actually don't have N right now, so N is also a question mark. R, you have a list that you can choose from, and then T is you already have it right here. So in order for you to figure out V of oxygen gas, you need to know the moles of oxygen gas. And the way you do that is to go from moles of potassium chlorate, because that's what's given to us, and go from that to moles of oxygen gas through stoichiometry. So here's an overview. Step number 1, use stoichiometry to calculate the number of moles of oxygen produced. And then you can use that to plug into PV equal nRT to convert the moles of oxygen to liters of oxygen. So let's go ahead and see how that would actually work out. Step number 1, use stoichiometry. So we start with 10.5 gram potassium chlorate. So I'm going to start with that, and I'm going to convert that to mole of potassium chlorate using the molar mass. And then I am going to convert moles of potassium chlorate to moles of O2 using the mole ratio, which is 3:2. So that should gives me that number for moles of O2 produced. Now this number is the missing N that we were talking about. So in PV equal nRT, we have P, we have T, we have R. We're missing volume and N, but we have just found N right here. So now we can use this new set of information, including our N number, to plug in PV equal nRT. So I'm first going to rearrange PV equal nRT to solve for V, and it should look like that. So now I have my given information. N is what we just solved in step number 1. R is I've chosen this particular one because the unit has atm in it, and our pressure has atm in the question. T is just a 25 degrees Celsius converted to Kelvin. P is what was given to us here. So I'm going to plug everything into the equation, and that should give me 3.14 liter of O2. let's do another practice problem. This one is not on your notes, so you don't have to copy this down. I just want to show you another way of how you can utilize stoichiometry and the ideal gas law to solve a problem. So in this problem, it's asking you to calculate the volume of hydrogen gas produced at 1.5 atm. So let's just go ahead and label everything. Here's volume. Produced at 1.5 atm, that's pressure. And 19 degrees Celsius, that's temperature. By the complete reaction of 26.5 gram of zinc with excess hydrochloric acid according to the below reaction. Okay, so same thing as before. The one piece of information does not belong. So this 26.5 gram belongs to zinc right here. And then all the other piece of information belongs to hydrogen gas here. And that's what we're trying to find. So just like before, step number 1 is to use stoichiometry to go from gram of one thing, in this case zinc, to moles of hydrogen gas. So I'm going to start with my given in this case, and it is 26.5 grams of zinc. So kind of a little spoiler alert, giving you the answer there. But from gram of zinc, I want to go to moles of zinc using the molar mass, and then using the mole ratio between zinc and hydrogen gas, which is just a 1:1, giving me this answer for mole of H2. Now, what should be the next step in this problem? The next step should be to use this new piece of information. So now this is our N. We have P, V, T, and N. I'm going to use PV going RT, and I'm going to first rearrange that to solve for V. And it should look like so. So now my new information, N, R, T, and P. And then last thing is to just plug in the equation, and you should get a final answer that looks like that, 6.47 liter of H2. Alright, the last example problem is the one in your notes, and I like for you to do the majority of the work here. I'll set up everything for you, and then you can see whether or not you understand the process by attempting this on your own. So first of all, let's label our 4 different variables in a gas law. So calculate, I'm reading the question that says calculate the volume of carbon dioxide gas. Volume, carbon dioxide gas produced at this much pressure and 30 degrees Celsius. By the complete decomposition of 182 gram of copper carbonate according to the below reaction. So I'm going to underline 182 gram because that is a mass that could easily be turned into mole. Now the question is, what is the chemical that should be in my final answer? So my final answer should be in carbon dioxide. So out of the 4 different information I just underlined, which one of those does not belong to carbon dioxide? 182 gram does not belong to carbon dioxide. And in fact, it belongs to copper 2 carbonate, which is this. So this is how you know you have to do stoichiometry, because they give you gram of one chemical, but they're asking you for the volume of a different chemical. So what should be my given for my stoichiometry calculation? What about what should I end up at the end for my stoichiometry calculation? So what I get started with is gram of copper carbonate. That's what's given to us, 182 gram. And you should get mole of CO2 at the end. Okay, so then going from gram to mole of copper carbonate, and then I'm going to use the mole ratio between copper carbonate and carbon dioxide, which is 1:1, and that actually gives me this answer. Okay, what is step number 2? Step number 2 is to rearrange PV equal nRT to solve for V. And it should look like that. Okay, let's go ahead and list out our list of given information, or the information we know, and our missing variable. So first of all, what is N? So N should be 1.473 mole of carbon dioxide, which is what we found in step number 1. And then what is R? R should be this number because the unit is torr, and that matches the unit we have here. Now then, what is our T? T is 30 degrees Celsius in converted to Kelvin. And lastly, what is my P? So P is 16.18.8 torr. And lastly, my missing variable, which is volume of carbon dioxide. You are going to plug all of this into the calculator. So go ahead and do that now. Hopefully you got this answer, 17.19 liter of CO2. And that is my final answer for that. The ideal gas law is very nice to work with in our calculations because it's pretty straightforward. There are quite a bit of limitations to it because, as the clue is in the name, very little things in our real life is in an ideal situation. So there are definite limitations to it, and meaning that it doesn't work well when the gas is at a very low temperature or at a very high pressure. The basis, though, of this law of the ideal gas law is based on what we learned in chapter 13, which is the kinetic molecular theory. Now, here are the assumptions again, just for as a review. So I'm not going to read out everything. Just go ahead and copy this onto your notes and read on your own. Now there's a couple more assumptions to this. And average kinetic energy is proportional to the Kelvin temperature of a gas. Remember that it has a direct relationship, so kinetic energy goes up, then Kelvin temperature also goes up. All right. One thing I didn't mention when I went over this in chapter 13 is that the collision between these particles are what we call elastic. Now, what it means is that when something is elastic, it means something, it bounces, just like how these little balloons bouncing off each other. And if it doesn't bounce, just like how you drop an egg like that on the ground, it's not elastic. So what it means is that when these particles collide with one another, they bounce it off of each other. Now, in spite of its limitations, the kinetic molecular theory explains most of the properties of the gases very well. That's why we can still use the ideal gas law to explain and do calculation in most situations. So, ideal gases versus real gases. What are the differences? So there's a few different types of differences. The first one being that gases behave ideally only at high temperature and low pressure. So if you take a look here at this graph, you'll find that the ideal gas is this line right here, and it has a nice direct relationship at all ranges of temperature. So even at a low temperature, it has a direct relationship. But when you look at the real gas, which is what is this dashed line here, in the lower range of temperature, it doesn't behave that nicely. It doesn't have that nice direct relationship. It only has that nice direct relationship after it have gone to a certain point. So this is at higher temperature where the real gas starts to behave like an ideal gas. Another difference is that in a real gas, volume of the particles is not actually negligible. So remember how I said that before, the particles of a gas are very small. So like how big this little particle is so small in comparison to like the distance between from one particle to another. So that's why in an ideal gas, we assume that the volume occupied by these little molecule, which is negligible, meaning that it doesn't really matter in terms of calculations. But actually in real gases, they do matter, and they do have like a distinct volume that's not negligible, meaning that we can't disregard it in our calculation. Another thing is that the particles behave differently in a real gas due to attraction and repulsion of each other. Recall from the kinetic molecular theory that says gas particles do not attract or repel each other. Now, this is the assumption that's not true for real gases. And in a real gas, these particles definitely do have some sort of attraction or repulsion from one another. So what you need to know from this slide is basically what I have here, and also make sure to read this little table that should be in your notes as well and understand it, and that might or might not pop up on your test. Okay, that wraps up notes 14.8 to 14.11. Thank you for your attention, and I will see you in class.